Hi, my name is Betsy Ogburn. I'm an associate professor of biostatistics at Johns Hopkins School of Public Health. And in this lecture, I'm going to give a brief introduction to causal inference. I'd like to first thank my fantastic PhD student, Brian Gilbert, who created these slides. And I'd also like to acknowledge the support to create this lecture from the SAMSI program on data science in the social and behavioral sciences. So here's an outline that you can refer back to in your own slides throughout. Very briefly, I'll first give an introduction to some core concepts and terminology, then talk about identifying causal effects, estimating causal effects, and some methods to deal with unmeasured confounding. Why do we care about causality? Why is causal inference such an important part of science and of statistics? I think there are a few big reasons. The first is that if we would like to use data to decide on future actions or future policies, we have to think about the effects that those actions will have on the world. And in order to inform those decisions, we need a kind of statistical analysis that recognizes causality and the effect of changes to the current state of affairs beyond associations. In some scientific contexts, causal methods can improve our understanding of mechanisms and of complex phenomena, because as opposed to a black box prediction of outputs given inputs, causal inference allows us to start to disentangle how variables interact with one another to create an output. And finally, in computer science, causal reasoning is recognized to be one of the huge limitations for current artificial intelligence systems. Our AI and ML, machine learning, are very good at prediction and pattern recognition, but one of the major features that's thought to distinguish between what artificial intelligence is currently capable of and human intelligence is understanding causality and causal inference. What is causation? Well, as we all know, it's not association. Correlation is not causation. An association or a correlation is a relationship between variables that we observe passively. And causation, at least the way that it's defined for the purposes of statistics and causal inference using data, is a relationship between variables that's determined by a hypothetical intervention on the treatment or exposure or cause that we're interested in. So causal inference asks questions like, if we could intervene to change X to some value, what would happen to Y? If we could intervene on a treatment or exposure, what change would we see in the outcome? And because we can't always actually go to the lab and perform the intervention that we're interested in an experimental context, we're going to have to define counterfactual variables or potential outcomes in order to talk about causality. So to make this more concrete, let's introduce a little bit of notation. So let's say we have a treatment or an exposure T. The classic example is that if T is equal to 1, that represents a treatment of some sort, and T equals 0 represents a placebo or a control condition. But T doesn't have to be binary, and it can really be any kind of exposure or treatment that you're interested in. And then Y is the outcome that we're interested in learning about the effect of T on. So we want to know the effect of T on Y. Y is the outcome, T is the exposure or treatment. A counterfactual outcome or a potential outcome is a random variable that tells us what would have happened if, possibly contrary to fact, T had been intervened on and set to some particular value, little t. So Y parentheses little t is a counterfactual or a potential outcome that is the random variable describing what would have happened to Y had treatment been set to little t. Potential outcomes are sometimes denoted with a subscript, so y subscript little t, but in this talk we'll do y parentheses little t. And the causal effects are comprised of counterfactuals. So for example, the ATE, the average treatment effect, is defined as the expected value of y1 minus y0. So this asks, what's the contrast between the outcome we would have observed in a world where everybody was giving treatment compared to the outcome in a world that we would have, the outcome that we would have observed in a world where everybody was given control. Some counterfactuals are factual, some potential outcomes are just simply observed outcomes, but we can only observe one of the possible counterfactual outcomes for each subject that we have data on. We observe the potential outcome for the treatment that that subject actually observed, but that leaves one or possibly more counterfactuals unobserved. And so we will need to use assumptions to link what we observe to the counterfactuals that we don't observe, but that we need to learn about in order to estimate causal effects. This brings us to identification. Using assumptions to link counterfactuals to the observed data is called identification, which means something slightly different in the causal setting from the way that identification is used in statistics more broadly. Identification is the expression of the causal estimand as a functional of the observed data distribution. So let's define these terms. A causal estimand is just the causal effect of interest. Most often it's the ATE, the average treatment effect, but it could be something more complicated like the distribution of the random variable y1. But basically the estimand is just the answer to the question that we're asking. A functional is like a function, except the input is a probability distribution or a collection of random variables. And the output is just a real number or a vector of real numbers. So for example, the ATE is a functional of the potential outcomes y1 and y0 because expectation is itself a functional. The observed data distribution is the data generating distribution for the data that we can actually observe. This is the outcome, the treatment, and possibly some covariates X. In contrast to the full data distribution, which is the data generating distribution for both the observed data and the counterfactual or potential outcomes. So it's the distribution of y1, y0, treatment, and covariates. And the idea is that a causal estimand is defined usually as a functional of the full data distribution, but we don't get to observe the full data distribution. We can only observe the observed data distribution. So we're going to use assumptions to link our causal estimand, which is a functional of the full data distribution, to a functional of the observed data distribution, which we can then estimate because using any tools from statistics, because that's what statistics is all about, estimating functionals of observed data. If we have non-experimental data, identification always involves strong, untestable assumptions. These assumptions can be made less strong. Identification can be less controversial. For example, if the assumptions are less parametric or non-parametric, or if the assumptions are really easy to justify based on subject matter, context-specific knowledge. But sometimes researchers also will use parametric assumptions like constant treatment effects or linear structural models, linear data generating models in order to get identification. Using parametric assumptions to identify causal effects can be risky, as summed up nicely in this quote from Cox and Donnelly. If an issue can be addressed non-parametrically, then it will often be better to tackle it parametrically. However, if it cannot be resolved non-parametrically, then it is usually dangerous to resolve it parametrically. One reason is that you can never use data that you have on hand to test parametric identifying assumptions, since identifying assumptions are used to link unobserved counterfactuals to the observed data. So a linear model might be a really good fit for the observed data, but that's no guarantee that it captures the full data distribution or that it provides a good link from the observed data to the unobserved counterfactuals. And another reason is that intuitions like, well, this parametric model approximates the truth, so even if it isn't quite right, my results shouldn't be too far off. That kind of intuition applies when you're using parametric models for estimation, but this intuition breaks down when those same parametric models are what's buying you identification of causal effects in the first place. So now we'll talk about some of the assumptions that are very commonly made in order to identify causal estimands from observational data. And these are all non-parametric assumptions. First is SUTVA, or the stable unit treatment value assumption. So SUTVA is just the acronym SUTVA. This actually comprises a few separate assumptions, but is often just listed as SUTVA. So the first component of SUTVA is the assumption that there's no interference. And this means that my treatment assignment can affect my own potential outcome, but it cannot affect anybody else's potential outcome. So this tells us that a potential outcome that has as its argument a single treatment, that the treatment corresponds to the same unit as the outcome, is well defined. If you have interference, if one person's treatment can affect multiple people's outcomes, then potential outcomes have to be indexed not only by a unit's own treatment, but also by all the treatments of the other units that can interfere with that unit. There's a growing body of literature on causal inference in the presence of interference. This assumption is easily violated in practice. For example, infectious diseases, or any kind of behavioral intervention, or any kind of information that could be passed from one person to another. But we won't talk about that in today's lecture. The second component of SUTVA is consistency. The consistency assumption says that if a particular unit is observed to have treatment little t, then that unit's observed outcome is equal to the counterfactual y of little t. And this assumption requires that there's only a single version of each treatment. So again, it's telling us that y parentheses little t is a well-defined random variable. Two other assumptions that together with SUTVA suffice for identifying causal effects are ignorability, or conditional ignorability, or the no unmeasured confounding assumption, which is sometimes abbreviated NUCA, N-U-C-A. This says that counterfactuals or potential outcomes are conditionally independent of the outcomes, conditional on measured covariates or measured confounders X. This can be violated when there's selection bias or unmeasured common causes, or colliders and collider bias. Crucially, the data that we can actually work with, the observed data, provide no evidence about whether the ignorability assumption is true or false. So this really has to be assessed using subject matter expertise to think about all of the ways, all of the types of variables that could induce dependence between the counterfactuals and the treatments, and making sure that data is collected on all of those variables and that they're well controlled for. And then there's the positivity assumption, which says that for every level of the covariates, there's a positive probability of receiving each possible treatment value. There is information in the data about this, and in fact, there's a distinction between theoretical positivity, which is what's stated here. This is a feature of the data generating distribution, and practical positivity, which is what you actually observe in your data. So what really matters is practical positivity. You want in your data for each level of the covariates for there to be some subjects who were treated and some subjects who were untreated, or some subjects who received each possible level of the treatment. And that's because that's the data that you're going to use to estimate causal effects. We will have to condition on or stratify by or otherwise control for covariates. And that means we're within levels of covariates, we're going to need data on both treated and untreated subjects in order to be able to use that data to estimate causal effects. Together, these three assumptions, SUTFA, conditional ignorability, and positivity, suffice to identify causal effects. They're not necessary assumptions. There are always other assumptions that you can make, for example, parametric assumptions, which I'll come back to in a little bit. Or, you could assume the causal effect is 5, and that is a sufficient assumption to identify that causal effect. It's not one that I would recommend using, but there are infinite combinations of assumptions that can identify causal effects, but these three form a very common framework for non-parametric identification of causal effects. There are lots of different languages or frameworks for talking about causal effects, but they all tend to rely on these same identifying assumptions. So the counterfactual, the potential outcome, the non-parametric structural equation model, or NPSEM, and the causal directed acyclic graph, or DAG, approaches to causal inference all use different terminology and different ways of expressing causal inference and identifying assumptions, but they typically rely on these same three identifying assumptions, at least for basic causal effects. The differences among these frameworks are primarily semantic. They're essentially mathematically equivalent. In particular, as I hope I've been emphasizing all along, potential outcomes and counterfactuals mean the same thing. A causal DAG is a graphical representation of a non-parametric structural equation model with independent errors. And DAGs can be extremely useful for assessing whether or not ignorability holds, the no unmeasured confounding assumption holds for a particular causal estimand. And they can also be really useful for deriving identifying expressions for causal effects from the observed data, but they don't actually change the fundamental framework for causal inference relative to any of the other approaches. Okay, so let's see how these three identifying assumptions, SUTFA, ignorability, and positivity, work to identify the average treatment effect. So the average treatment effect is a functional of the counterfactuals, not of the observed data. But using these assumptions, we can write it as a functional of the observed data only. So first, we use iterated expectation to condition on X. X is the covariates that make ignorability true. So these are covariates that suffice to control for confounding. So by assumption, ignorability holds conditional on X, and that means that potential outcomes are independent of treatment, conditional on X. So that means that we can add a conditioning event for treatment to this conditioning event of X. And that's what I've done in this third line. Now, by consistency, we can turn the potential outcomes into observed outcomes. And we still need positivity. Positivity ensures that the conditioning events here have positive probability, and therefore that these conditional expectations are well defined. And now we have a functional of the observed data alone, and we have proved that it's equal to the causal estimand that we're interested in, the ATE, under these three assumptions: ignorability, SUTFA, and positivity. common alternative to the non-parametric identification on the previous slide is to estimate or identify the ATE through a linear model. So we can assume that Y is linear in the treatment and the covariates, and then interpret the parameter beta, the treatment parameter, as the causal effect of the treatment on the outcome. But this requires stronger assumptions than the strategy on the previous slide. So first of all, this requires the model to be correctly specified, this linear model to be correctly specified for, this is written as a model on the observed data, and it has to be correctly specified for the observed data, and correctly specified, not just approximately correctly specified. And this is a really strong assumption, especially if X is high dimensional. We have to get the functional form exactly correct. And then this also implies models for the counterfactuals, and these also have to be correctly specified. So Y0 and Y1 both have to be linear in the covariates. In contrast, just using a linear model for estimation, for example, if I go back a slide, to estimate the conditional expectations in the very last line here, that only requires a linear model to be a good fit for the observed data. But using a linear model to identify causal effects requires it to be a true model for the counterfactuals. Note that these implied linear models for the counterfactuals are totally untestable. So you have to have a lot of subject matter knowledge to be very confident that these counterfactuals themselves are linear, whereas using a linear model for estimation is testable. We can test that it's a good fit for the observed data. Randomized trials are generally considered to be the gold standard for causal inference, and the identification strategy that we went through above shows why. In a randomized experiment where treatment assignment is determined by a flip of a coin or a random number generator, treatment by design is independent of all individual characteristics. So this means that ignorability holds by design, and it holds unconditional on any covariates, and positivity also holds by design, because there's going to be a positive probability of treatment for all covariates, independent of those covariates. We've talked about the ATE, or the average treatment effect, but there are a bunch of other causal effects that are maybe of interest. The average effect of treatment on the treated, or the ATT, is defined as the expected difference in counterfactuals conditional on t=1. So the idea is that in an observational study, the people who receive treatment may be systematically different from the people who don't receive treatment. That's the nature of confounding. And maybe we're only interested in knowing the effective treatment among the types of people who tend to receive treatment. That would be the effective treatment on the treated, or the ATT. The SATE is the sample average treatment effect, and the idea here is that the if we have a truly random sample, then the SATE is equal to the PATE. The average treatment effect is sometimes called the population average treatment effect, or PATE, to differentiate it from the SATE. But if we have a non-random sample, if the people in our study differ to some extent from the population that we're interested in, the target population, then the sample average treatment effect might actually be different from the population average treatment effect. And so it has its own definition in that case. And the conditional average treatment effect, or CATE, is the treatment effect conditional on covariates. Usually these would be covariates that predict treatment effect heterogeneity. So CATE is often of interest in personalized medicine, where researchers are interested in finding the covariates that predict subpopulations that can especially benefit from treatment or something like that. And of course, these are all defined on the additive scale, but all of these treatment effects can be analogously defined on the odds ratio or risk ratio scales. Okay, so now let's talk about what can go wrong if you try to estimate causal effects without carefully assessing the identifying assumptions, or if, despite careful assessment, some of the identifying assumptions fail to hold. Generally, confounding bias is what people have in mind when they say correlation is not causation, although, as we'll see, that's not the only way that things can go wrong. But broadly, confounding bias can mean any violation of the assumption of ignorability. Usually, though, what people have in mind with confounding bias is an unmeasured common cause, or a common cause of treatment and outcome that is not adequately controlled for. A common theme here is when the worst off subjects are most likely to receive the intervention, or vice versa. And on the next slide, we'll talk about a medical example involving treatment for kidney stones. So this is a paper that compared open surgery to a less invasive procedure called percutaneous nephrolithotomy to treat kidney stones. Group 1 in this table is patients with small kidney stones, and group 2 has large kidney stones. As you might expect, people with small kidney stones are more likely to have the less invasive procedure, and people with large kidney stones are more likely to have open surgery. But smaller kidney stones are also associated with better outcomes overall. So if you fail to control for group membership, that is, if you fail to control for kidney stone size, it looks like open surgery has a lower success rate than percutaneous nephrolithotomy. But within each group, open surgery had a higher success rate. So the crude effect is picking up on a difference in the distribution of kidney stone size between treatment arms, when in fact the causal effect of open surgery is to improve outcomes, as you can see, as soon as you control for kidney stone size. This is an example of Simpson's paradox, where the crude estimate of the effect is actually in the opposite direction from the true effect. But confounding bias doesn't have to flip the sign of the effect, it can just change its magnitude as well. Another source of bias is collider bias, where instead of having a common cause that is a confounder of treatment and outcome both cause a common effect, which is conditioned on. And conditioning on that common effect, or collider, induces dependence between treatment and outcome that's non-causal, and so that can bias causal effect estimates. You can condition on a collider by selection, that is, the study participants that happen to be included in a sample, and then it's known as selection bias, or by adjustment, where you inadvertently control for a collider thinking that it will help to control for confounding, but in fact it induces collider bias. So colliders should never be included in the covariates that are used to control for confounding. Just like an unmeasured common cause violates ignorability, conditioning upon a collider violates ignorability. It induces dependence between the potential outcomes and the treatment assignment. A really simple kind of canonical example is that in order to be an elite basketball player, you usually have to be really tall. But if you're not really tall, you can sometimes compensate with really amazing other skills, like being extremely fast. So if you condition on being an elite basketball player, that's the collider here, it induces extra dependence between height and speed. So it appears, if you look at just the group of people who are elite basketball players, it will appear as though height and speed are more closely related than in fact they are in the general population, because as soon as you find an elite basketball player who's shorter than average, you know that you have really good reason to think that they're probably very fast. Another example is differential loss to follow-up. So suppose a treatment for a condition has some unpleasant side effects, and patients tend to drop out of a study if either the condition or the side effects become burdensome, and especially if both become burdensome. So patients who have the side effects but remained in the study through the end of follow-up are less likely to also have the condition. And this can bias the apparent association between the treatment and condition if your study sample is comprised only of those subjects who never drop out, who make it through the end of follow-up. Okay, so now we've talked about identifying causal effects, and in particular, we showed how under the assumptions of SUTFA, ignorability, and positivity, we can map the ATE, the average treatment effect, onto a functional of the observed data. And now we're going to talk about estimation, how to estimate that functional of the observed data. So remember that the ATE, which is the contrast of expected potential outcomes or counterfactual outcomes under treatment and under control, is identified by this double expectation functional of the observed data. So the expectation of the expectation of y given x and t. Those inner expectations are just the normal type of conditional expectation that we know very well how to estimate in statistics. And in particular, we can just use a regression model, a parametric or a non-parametric regression model, to estimate the expected value of y given x and t. This is referred to as the outcome regression model. And then once we have estimated the expected value of y given x and t, so that is a function of x and t, I'm going to call it f of x and t, we can just standardize that by x. So we want to take the expected value of that conditional expectation, and the way to do that is to integrate over x or sum over x, and in particular, since x is just observed covariates, it's not something that we want to intervene on, we can just take the sample average, and that is standardizing by the empirical distribution of x. So just to describe this one more time operationally, to estimate this outcome regression functional, we can fit a regression model for the conditional expectation of y given x and t. Then we can take the sample average of the conditional expectation of y given x and t equals 1 and subtract off the sample average of the estimated conditional expectation of y given x and t equals 0. And this estimation approach is known as the outcome regression approach, the standardization approach, or the G formula approach. There's another alternative way to estimate the ATE, and actually it's based on an alternative way to identify the ATE. And it turns out that using those same assumptions of ignorability, positivity, and SUTFA, there is another identifying expression for the ATE. So first, note these two equalities, that t divided by the probability that t equals 1 given x, its conditional expectation given x is 1, and the same with 1 minus t divided by the probability that t equals 0 given x. This is like t is like an indicator of receiving treatment, and an indicator divided by its expectation has expectation 1. Now, under ignorability, positivity, and consistency, we can take the ATE and identify it with this functional of the observed data at the bottom here. So this first line is just like before, iterated expectations. The second line, in the second line, I'm multiplying each potential outcome by 1, essentially. And I can do this because I know by ignorability that T is independent of the potential outcomes or the counterfactuals conditional on X. So this truly is just multiplying by a function that has expectation 1. Now, by consistency, I can replace the potential outcomes or counterfactuals with the observed outcome Y. And I can do that because I'm multiplying Y by the indicator that treatment is 1 or the indicator that treatment is 0. So I'm not losing the fact that that first Y refers to the potential outcome Y1 and the second one refers to the potential outcome Y0. And now I can drop the inner conditional expectation again by iterated expectation. This functional of the observed data suggests an alternative estimator for the ATE. This is the inverse probability weighted estimator. So I'm going to define the propensity score, which is the probability that treatment or exposure is 1 given X, and I'll label that E of X. And now I am just using that same identifying expression, but instead of the probability of treatment given X, I'm plugging in an estimated propensity score. And then to take the expectation, I'm again just taking the empirical average. We can estimate propensity scores with logistic regression or really with any kind of binary regression model. In some settings, it's easier to correctly specify a model for the propensity score than it is for the outcome regression. And that would make inverse probability weighting a better approach to estimation than the outcome regression approach that we talked about before. In particular, if treatment assignment is the result of some known process, especially a process that's written down. So for example, if doctors are using medical records to decide what treatment to give a patient, they might be able to tell researchers very clearly exactly what covariates go into the propensity score and what role they play. Or even better, if an algorithm is being applied to some measured covariates on patients and to spit out a treatment recommendation, then the propensity score model is known. And obviously, that's easier to correctly specify than an unknown outcome regression model. One challenge for inverse probability weighted estimators is that very small or very large weights can really blow up the variance of this estimator. So if some patients have very small propensity scores, that's going to result in the inverse being really large. So you can see the propensity score is in the denominator of the estimator here. And so if the propensity score takes on a very small value, then T times Y divided by the propensity score is going to be huge. And that can allow some subjects to have outsized influence on the estimator, and it really increases the variance of the estimator overall. So it's pretty common when using inverse probability weighted estimators to trim observations with extreme weights. A challenge to that is that that changes the population over which you're estimating the ATE, and can change the interpretation and the generalizability of the effect estimates that you get out of your analysis. The propensity score is what's known as a balancing score, meaning essentially that if ignorability holds conditional on X, then ignorability also must hold conditional on the propensity score. So this is saying that the propensity score as a function of X suffices to control for all confounding due to the covariates X. The inverse probability weighted estimator can be interpreted as creating a weighted pseudopopulation in which treatment is effectively randomized. And there's a great explanation of this in the free online book by Miguel Hernan and Jamie Robbins. And there's also a large literature on methods that match or stratify by propensity scores instead of weighting by propensity scores. So now that we've talked about outcome regression approaches and propensity score based estimators, we're going to talk about how we can combine an outcome regression model and a propensity score model to the advantage of the estimator's accuracy. So suppose we have an estimator F hat for the outcome regression and an estimator E hat for the propensity score model. And ideally, both of these models would be correctly specified, and F hat would converge to the true outcome regression F, and E hat would converge as n goes to infinity to the true propensity score model E. But we're going to show how we can get consistent estimates even if only one of these two models is correctly specified. So for now, let's say that F hat converges to some limit, F tilde. We hope that's the true F, but it may not be. And E hat converges as n goes to infinity to some limit, E tilde. Again, we hope that's the true propensity score model E, but it may not be. And we're going to talk about an estimator that involves both of these estimated functions. This estimator is called a doubly robust estimator, or I'll denote it with a DR, ATE sub DR for doubly robust. It involves two main terms. The top green one estimates the potential outcome under t equals 1. And the bottom red term estimates the potential outcome under t equals 0. Each of these terms itself involves two terms. So this first term here is the propensity score estimator, the IPW estimator, inverse probability weighted estimator of Y1. Here, this is the inverse probability weighted estimator of Y0. And then the second term involves the outcome regression plus a kind of residualized version of treatment. And here again, the outcome regression plus times a residualized version of treatment. I'm going to call this first line mu1. This estimates the expected value of y1, and the second line is mu0. This estimates the expected value of y0. Under some regularity conditions that are very technical, but just allow us to replace E hat and F hat with their probability limits, E tilde and F tilde, we can get that mu1 converges as n goes to infinity to this expectation. By consistency, we can replace y with the potential outcome y1 when y is multiplied by the indicator that treatment is equal to 1. And now after some algebra, we get this expression that is the expected value of y1, which is what we would like mu1 to converge to, plus this error term. And so the question is, when will this error term be 0? Mu1, our estimator of the expected potential outcome y1, will converge to what we want it to, the expected outcome, the expected counterfactual y1, whenever this second term is equal to 0. So that's what we're going to look at next. So first, let's look at what happens to this error term if the propensity score model is correctly specified, which means that the probability limit of E hat, our estimated propensity score model, is the true propensity score model E, or E tilde is equal to E. Then by some clever use of iterated conditional expectation and some algebraic manipulation, we can reduce this error term to something that includes in it the expected value of t minus e of t given x. And this whole thing is given x. So this is by definition of E of x, by definition of the propensity score model, this is going to be 0. And since this multiplies the rest of the expression, we are going to get that the entire error term is equal to 0. And this holds no matter what the probability limit of the outcome regression model is, no matter what f tilde is, because we are multiplying, because this error term includes a factor that is by definition equal to 0, the entire expression is going to be 0. So by the logic above, our doubly robust estimator mu1 will converge to what we want it to converge to, the expected value of the counterfactual undertreatment equal to 1, if the propensity score model converges to the truth. All right, what about if the outcome regression model is correctly specified? Then the probability limit of f hat is f, the true outcome regression model, or f tilde equals f. And again, by some clever use of iterated expectation and algebraic manipulation, we get this expression here. Y1, the expected value of y1 minus the regression function, which is defined as the expected value of y given t equals 1 and x, which is equal to the expected value of y1 given t equals 1 and x, that this expectation is then by definition equal to 0. And again, we have an expression, we've reduced the error, this big error term, to something that has a product in it that is by definition equal to 0 whenever f is truly capturing the conditional expectation of y1 given t and x. So again, if the outcome regression model is correctly specified, then the estimator will be consistent no matter what the probability limit of the propensity score model is. So we've just seen that our estimator of the expected value of y1 converges to the true expectation of y1 if either the outcome regression model is correctly specified or the propensity score model is correctly specified. And the same argument applies for our estimator of the expected value of y0. So this means that we can consistently estimate the average treatment effect if either the outcome regression or the propensity score model is correctly specified. And if they are both correctly specified, then we have an efficient estimator, meaning it has the smallest variance from a class of estimators. This property that we get a consistent estimator if either the outcome regression or the propensity score model is correctly specified is known as double robustness. And one really useful feature of double robustness in this setting for the ATE and for many other estimands is that the rate of convergence of our estimator of the ATE is the product of the rates of convergence of the two nuisance functionals, which are the outcome regression and the propensity score model. And so this means that we can use machine learning estimators for the outcome regression and the propensity score model and still get root n consistency of what for the parameter that we really care about, which is the ATE. So I've talked a little bit about about what the double robust estimator is. To do inference, we need standard errors for this doubly robust estimator, and there are a number of methods available. You can, in theory, bootstrap, but you have to be careful to bootstrap the entire procedure. So in each bootstrap sample, you estimate the propensity score model, the outcome regression model, and then the doubly robust estimator of the ATE. Or there are analytic standard error estimators available using M-estimator theory and influence functions. So far, we've been assuming that the typical assumptions of causal inference hold. And in particular, we know that in practice, ignorability will almost never hold exactly. In many, many settings, we can't even enumerate all the possible confounders of the treatment outcome relationship, let alone measure them accurately and control for them properly. So in the last part of this lecture, I'm going to talk about some strategies for dealing with, for estimating causal effects in the presence of unmeasured confounding. So I'll briefly talk about three types of strategies: sensitivity analyses, instrumental variables, and natural experiments. The observed data itself cannot provide any evidence about the existence of unmeasured confounding. Whether or not all confounders were measured and controlled for is not something that you can ever check. But we can learn things like how much unmeasured confounding would be needed to undermine the result of this analysis. And that's the type of question that sensitivity analyses ask. A sensitivity analysis quantifies how sensitive or robust your conclusions are to departure from the assumptions that you made in your analysis. And in this case, the assumption that we will use a sensitivity analysis to probe is the no unmeasured confounding assumption, or the ignorability assumption. So we can't test for the existence of an unmeasured confounder, but we can posit the existence of an unmeasured confounder and see how much the strength of its confounding changes what we believe about the causal effect that we're interested in. If a reasonable amount of unmeasured confounding does not change our substantive conclusions, then that's additional evidence in favor of those conclusions. There are lots of techniques for running sensitivity analyses. Some of them involve simulating an actual confounder and its relationship to the exposure and the outcome. Others, like Rosenbaum bounds or e-values, are analytic analyses that you can kind of run on top of your existing analysis that will tell you how strong would confounding have to be in order to overturn the results of this analysis. So sensitivity analyses are about how robust your conclusions are to the presence of unmeasured confounding. And the rest of the techniques we'll talk about are ways to get around unmeasured confounding. The first technique we'll talk about is using an instrumental variable, or an instrument. In this context, an instrument is a variable that's associated with the treatment of interest, but is not confounded with the outcome and has no direct effect on the outcome. It only affects the outcome through the treatment. So you can see that in this graphical diagram, where Z is the instrument and Z causally affects the treatment, but does not affect the outcome Y directly, only through T. And we'll see how the existence of such an instrument can recover valid causal effects of T on Y, even though in this case T and Y have an unmeasured common cause. So there's unmeasured confounding for the treatment outcome relationship that we're interested in, but the existence of this instrument Z is going to help us get around that. To give a very high level intuition for how instrumental variable analyses work, because the instrumental variable is unconfounded with the outcome, we can estimate the effect of Z on Y. And then we can scale this by the Z to T relationship to get an estimate of the effect of T on Y, or the part of the effect of Z on Y that is through T. A classic example of an instrument comes from econometrics. demand elasticity, or the effect of price on demand, is often thought to be confounded. But for certain types of agricultural products, weather can be used as an instrument because weather affects price, which is the treatment of interest. It affects price through supply, but it does not affect demand directly. And so an instrumental variable analysis that uses weather as an instrument can recover the estimates of demand elasticity for agricultural products. Another example that we'll talk more a bit about on the next slide is in cases where there's treatment non-compliance, treatment assignment is an instrument for treatment received. So if a doctor tells you to take a particular medication and some people follow those instructions and others don't, then the treatment assignment might be unconfounded, but treatment received or actual compliance with that assignment could be confounded. And then the effect of a phenotype on an outcome might be confounded, for example, by shared environmental determinants of the phenotype and the outcome. But a SNP, a single nucleotide polymorphism associated with the phenotype, can be thought of as having been randomized during recombination of parental DNA at conception and is unlikely to be associated with any non-genetic outcome except through the phenotype. And this is a use of instrumental variables known as Mendelian randomization. Instrumental variable methods are useful even in randomized clinical trials or randomized experiments where the treatment assignment is truly randomized. And this is because if some subjects do not adhere to treatment assignment, and if they're systematically different from subjects who do adhere to treatment assignment, then whenever there's non-compliance, the treatment effect could be confounded. And it's this setting that has given a lot of the terminology to IV methods. So you can imagine 4 different types of subjects in this randomized experiment. Compliers do what they're told. So when they are assigned to treatment, that is when their instrument is 1, the instrument here is treatment assignment, then they take treatment, that is their treatment is 1. So when Z is 1, T is 1. And similarly, when they're assigned to control, when Z is 0, they stick with control. They don't take the treatment. So when Z is 0, T is 0. Always takers take the treatment no matter what their instrument tells them to do. So for always takers, T is 1 regardless of what Z is. Never takers never take the treatment. So T is 0 regardless of what Z is. And then defiers are a perverse group of people who take treatment only when they're told not to. So if Z is 0, then T is 1. And if Z is 1, then T is 0. And these groups of people are sometimes referred to as principal strata. The term principal stratum refers to a group of people defined kind of causally and not in terms of things that we can actually observe about them. So because for any given person, we only see them receiving 1 treatment assignment or 1 instrument value, we don't know what they would have done had they had a different instrument value. So we can't identify from the data who the compliers, always takers, never takers, and defiers actually are. But arguably the group that we care most about of these 4 principal strata are the compliers. They're the ones for whom if we can change their instrument, we can also change their treatment. They're the ones who will comply with what the doctor tells them to do. It turns out that under some assumptions, we can identify the causal effective treatment among the compliers, or the complier average causal effect, or the case. case is also sometimes called the local average treatment effect, or LATE, where local refers to the fact that it's the average treatment effect among the compliers. It's also sometimes called the CATE, the complier average treatment effect, but I'll try to stick with case. So the assumptions that allow us to identify the complier average causal effect in IV settings are ignorability. In this case, though, it's the treatment assignment or the instrument that is unconfounded. So the instrument Z has to be unconfounded, has to have an unconfounded relationship with Y. The exclusion restriction says that the instrument Z only affects the outcome through the treatment. So there's no direct effect of the instrument on the outcome. And instrumentation says that Z truly does affect T. So, if we have a candidate instrument that we think will help us identify causal effects, if it turns out that Z has no relationship to the treatment or exposure that we're interested in, T, then all bets are off. So the instrumentation assumption entails that Z truly does have an effect on T. And then the monotonicity assumption is the assumption that there are no defiers. And I should say that I'm using treatment assignment and treatment received language here because that corresponds to these principal strata being called compliers, always takers, never takers, and defiers. But really, these are just labels attached to any instrument, exposure, or treatment and outcome. Okay, so informally, the way that these assumptions allow us to identify the case or complier average causal effect is that, well, first of all, because there are no defiers, we can say that Z, the instrument, can only affect the outcome among compliers. Z can have no effect on the outcome for never takers or always takers because the only way that Z affects outcome is through the treatment, and for never takers and always takers, Z doesn't affect the treatment. So if we look at the intent to treat effect, which we can estimate because it's unconfounded, so this is just the causal effect of Z on Y, we see that the intent to treat effect is just the case, the effect that we're interested in, multiplied by the probability of being a complier, or the proportion of compliers in our study population. And so this tells us that the case is equal to the intention to treat effect divided by the probability of being a complier. So if we can identify the probability of being a complier, we're good to go, because again, the intention to treat effect is just the causal effect of Z on Y, and by assumption, that's unconfounded and is identified from the observed data. Under the assumption of no defiers, our population is comprised entirely of compliers, always takers, and never takers. And if Z is randomized, or otherwise we could do this conditional on observed confounders of the ZY relationship, we can identify the proportion of always takers with the probability that T is equal to 1 given Z is equal to 0. We can identify the proportion of never takers with the probability that T is equal to 0 given Z equals to 1. And this allows us to identify the probability of being a complier, or the proportion of being compliers. And so this tells us that the case is identified by, here in the numerator, I've got the intent to treat effect, and in the denominator, I have the probability of compliers. We can estimate this parametrically with two-stage least squares, or using plug-in estimates for the expectations in the numerator and denominator. And there are also semi-parametric and doubly robust estimators available. There are two challenges for instrumental variable methods. The first is if the instrument is weak, that is, if the relationship between Z and T is not very strong. In this case, the denominator of the IV estimand on the previous slide will be close to 0, and that can result in unstable estimates. The other challenge is that, or it's not so much a challenge as a kind of feature of the estimand that we're getting out. The Complier average causal effect is the causal effect among a population that we can't identify. We don't know who in the world are compliers, and so it can make it hard to think about using these effects for policy decisions. On the other hand, the compliers are precisely the group of people for whom we know how to toggle their treatment value and for whom we know how to have a causal effect on their outcome. And so there's some thought that we're getting at something fundamental and mechanistic and explanatory when we estimate this causal effect. Now we'll talk about a larger class of methodologies for dealing with unmeasured confounding called natural experiments. Natural experiments exploit variation in treatment or exposure that is random or effectively random, even though it's not controlled by any researcher or by design. It can be really easy to obtain quite large samples for natural experiment analyses, for example, using administrative data. But all natural experiment methods rely on strong assumptions, often parametric, that have to be assessed very carefully in order to believe causal inferences that come from these methods. As an example of a near perfect natural experiment, in 2008, Oregon opened a waiting list for 10,000 spots in the Medicaid insurance program for low-income adults. 90,000 people signed up to join, and the state decided to issue a random lottery in order to choose 10,000 from among those eligible 90,000 people. So this is a case where treatment, in this case, receiving Medicaid, truly was randomized. It just wasn't randomized for the purpose of research or by any researcher or study design. And so for the effect of receiving a spot in the Medicaid program on various outcomes, these data can be analyzed just like a randomized trial, where the 80,000 people who were eligible but did not receive spots in the program are the control subjects, and the 10,000 who did receive spots are the treated subjects. Most natural experiments are not quite this clean and require some extra statistical finessing in order to turn them into what looks like a randomized experiment. But if you're really lucky, you'll be interested in studying the effect of some kind of exposure that was turned into a lottery by a government agency. Regression discontinuity is a way of kind of extracting an as-if randomized experiment from settings where there's some arbitrary cutoff or threshold that determines whether people are eligible for the treatment or not. So, for example, if a school admission requires a particular test score on an exam in order to be eligible for admission, then exactly where that cutoff falls, whether it's 80 points or 90 points, or rather whether it's 80 points or 81 points, is a kind of arbitrary decision, or the income cutoff for Medicaid eligibility might be arbitrary up to a certain point. The idea being that if there are individuals who are very close to the threshold on either side of the threshold. They're probably really similar to one another. Students who score 79 versus 81 points on an exam, or people whose incomes fall within $20 of a month of one another. Those are likely to be very similar people. So the diamonds are the subjects who fall below the cutoff. The triangles are the individuals who fall above the cutoff, and are on one side of the cutoff. Individuals are eligible for and may receive the treatment of interest, and on the other side they don't. And the idea is that the individuals who are closest to the cutoff, so the green diamonds and the green triangles, may be really comparable to one another, even though on the whole, the diamonds are not comparable to the triangles. Regression discontinuity analyses apply a local regression around that cutoff point and look for a sudden jump or a discontinuity. That's where the name regression discontinuity comes from. These threshold cutoff scenarios are huge problems for standard causal inference because they violate positivity. If you fall below the cutoff, you're only eligible for one particular treatment assignment, and if you fall above the cutoff, you're only available for the other treatment assignment. But the idea that people just above and just below the cutoff are comparable to one another obviates the need to use other kinds of extrapolation techniques to get around this positivity violation. The fundamental assumption that drives regression discontinuity designs is the assumption that the cutoff is arbitrary, not globally, but locally. So the choice of a cutoff of 80 versus 81 for a test score is arbitrary. And this is what entails that people on each side of the cutoff are exchangeable with respect to everything but the exposure that they received. The biggest risk for this assumption is the possibility that the cutoff can be gamed. So for example, suppose there's a cutoff in some medical risk score that determines whether you get a particular treatment or not. If there's some subjectivity that goes into computing that medical risk score, and then it could be the case that a doctor who just feels that this patient would benefit from the particular treatment could artificially inflate or deflate the risk score, even possibly subconsciously. Test scores, on the other hand, are generally not gameable. You know, everybody does their best on the test, and whether you happen to achieve a score of 79 versus 81 is not something that you can directly control. Usually causal effects are estimated parametrically using regression discontinuity designs, but non-parametric methods are also available. So here's an example of a regression discontinuity analysis that looks at whether there's an incumbent effect on being elected to the US Senate when running for a second or third or subsequent term. So elections turn out to be great regression discontinuity instruments because there's a clear and arbitrary cutoff that is, if your margin of victory is greater than 0, you become the elected official, and if it's less than 0, you don't. And you can imagine that elections that are very, very close, in elections that are very, very close, the candidates that win and don't win are essentially exchangeable with one another. But this analysis showed that candidates who fall just on the greater than 0 margin of victory side of that cutoff have a much higher probability of winning subsequent elections than candidates who fall just on the margin of victory less than 0 side of that cutoff. Estimating the effect of the running variable, the regression discontinuity causal effect, requires selecting a kernel, which essentially determines how observations far from the cutoff point are downweighted. The simplest kernel is a rectangular kernel, which essentially only considers individuals within a specified distance from the cutoff. So for example, only including those green diamonds and triangles on that first toy example picture. But other kernels can increase the, can optimize a bias variance trade-off where including some information from points that are farther from the cutoff can decrease variance even if it introduces some bias, and a smart kernel can weight those effectively. An interrupted time series analysis is really similar to regression discontinuity, where the cutoff is in time. So if we have data on units before and after an intervention is suddenly applied at a point in time, we can compare those units to themselves before and after treatment. Because the populations are the same pre and post intervention, this doesn't map onto a randomized experiment in quite the same way that regression discontinuity does. But the idea is otherwise very, very similar. The example in these graphs here is from an indoor public smoking ban that was implemented in 2005 in Sicily. And on the y-axis, we're looking at acute coronary events. And the idea is, if we believe this graph on the right, there is a sudden drop in coronary events right when the ban is implemented. And this suggests under some very strong assumptions, a causal effect of the public smoking ban on the acute coronary events. Difference in differences approaches are very similar to interrupted time series, but with the addition of a control group. The control group never sees that sudden implementation of the intervention and can be used to estimate secular trends that could confound the pre-post exposure comparison using just an interrupted time series approach. So for example, if coronary heart disease rates are changing in Sicily over time, then the sudden change that looks like it's due to the implementation of a smoking ban could actually be due to those secular trends. And if we had a control group that never saw a smoking ban implemented, we would be able to estimate those secular trends and, under some assumptions, subtract them off. The key assumption there is the assumption of parallel trends. This is the assumption that in the absence of treatment, the treated and untreated individuals would have had, or treated and untreated groups would have had parallel time trends. And this assumption is stronger than it might appear at first. And in particular, it implies that all confounding is additive. But this assumption replaces the assumption of ignorability, because essentially we're going to be able to estimate the shape of the confounding curve using the control group and subtract it off from the treated group, the effect that we see that in the treated group, which could possibly be confounded. So in this diagram, we see that the treated group is in red and the control group is in green. And the naive estimate would just look at this post-intervention outcome and subtract off the pre-intervention outcome and estimate the effect of the intervention to be this difference here. But this difference is in fact a combination of a secular trend. The red line was increasing even before the intervention, and under the parallel trend assumption would have continued to increase in a way that continues to parallel the green line. And so the true effect is this naive estimate, taking this and subtracting off this. That's the naive estimate minus the component of that that's due to the secular trend. And we can estimate the component due to the secular trend by looking at this green line and taking the outcome at the end of follow-up and subtracting off the outcome at the beginning of follow-up. And that is the secular trend, or the confounding due to secular trends. And when we subtract that off, we get the true effect, which is the post-intervention outcome minus where the pre-intervention outcome would have, where the post-intervention outcome would have been had the intervention not been implemented. When there isn't a single control group that you think will capture the secular trends well for your intervention group. So if you think that you've got many candidate control groups, but none of them are expected to be precisely parallel with the control group, then with the intervention group, then the synthetic control approach is a kind of augmentation of the difference in differences approach. The synthetic control method creates a weighted average of many different control units that are used to approximate what would have happened in the treatment group had the intervention never been implemented. So it's a weighted average of control units that approximate Y0, the potential outcome that we would have seen in the treatment group if this intervention had never been implemented. Just like difference in differences, under the hood, this method relies on strong parametric assumptions, despite being really intuitive and seemingly quite simple. In particular, the unexposed counterfactuals for all units have to come from a linear factor model, and the treatment effect has to be additive. In a famous example, Abadi et al. Used synthetic control analysis to look at the effect of the passage of Proposition 99 in California, which was a tobacco control package of legislation, the effect of the passage of Proposition 99 on tobacco consumption in California. And you can see in this left-handed graph that this is comparing tobacco consumption in California with candidate control states. None of these states is a perfect match for California in the time period before the passage of Proposition 99. And if we don't have perfectly parallel trends before the passage of Proposition 99, then there's a good chance that that the parallel trends assumption would be violated for the entire analysis. In the right-hand panel, you can see the synthetic control that Abadi et al. Created as a weighted average of these, I believe it's 35 control states. And this weighted average perfectly captures the trajectory of tobacco consumption in California before the passage of Proposition 99. And if we believe the assumption that it would have continued to perfectly capture that trajectory in the absence of Proposition 99, then we can look at the difference between this point and this point as the causal effect, or actually any points along these lines as the causal effect of the passage of Proposition 99 on cigarette consumption. And that concludes this lecture. The following slides are bibliographies for your references. And thank you for listening.